Hello students, today I am going to give you some important points. Mostly I have covered all over most of the points from this lesson. Okay, uh, the lesson is system of particles. Okay, are you clear? Let's start. Already you should have completed this lesson. Just I giving you the formulas. The most of the formulas I have covered. Okay, now first formula is the center of mass we are going to find. Okay, so first we will write it. Center of mass means if n number of particles combine together to form a single mass system is what the a system of particle. Okay, so for that we have a particular center of mass. If I take this circle, its center of mass depends on this point, like that. Okay, so the center of mass varies with the shapes. Like if you take triangle, the center of mass is over here, like that. But you can't say that the center of mass means it will be lying on the center alone. It varies. For example, if you see this rod, okay, where would be the center of mass? Either here or middle piece is here, you think? No, the center of mass lies over here. Okay, like that the center of mass varies. So we are going to find the position, the coordinate of the center of mass. What's the formula going to be in that? Okay, if n number of particles combines, n number of particles is combining to form this single system. Okay, so how will you write the formula RCM? This is the position of the center of mass. This point is m1 r1, the first particle mass, and this particles, the first particle distance from the origin. Okay, like this. If you say this is the coordinate, y coordinate, x coordinate, so like this it goes. Okay, are you clear? So if it's m1 you take, so this is the point r1 from the coordinate. That's what I writing here. m1 r1 plus m2 r2, it goes on mn rn, you write it like this. The total mass m1 plus m2 plus goes on mn. Are you clear? Are you clear? Shall we move further? And one more important point, if the particle is not subjected to any external force, in the absence of any external force, the velocity remains constant. Okay, no external force, the center of mass won't change. Mostly the center of mass won't change, and if there is no any external force, then velocity remains constant. Also you know that the momentum is product of mass and velocity. So the total mass is m1 r1, m1 m2, the total mass, correct? So the total, the velocity, if you take the total velocity, the center of mass velocity, okay, this is the velocity of the center of mass. Are you clear? So VCM is the center of mass velocity, and it will be momentum times momentum by total mass. So if you rearrange this, total mass, this is the total mass. Okay, total mass into velocity of the center of mass equals to momentum. This is one more point. So the momentum also, how we can write is P1 plus P2 plus goes on till Pn equals to total momentum. That's what over here. Okay, clear? Now shall we move on to the next formula? I told you, no, your VCM, how to find the VCM. So this is the second formula, momentum formula. How to find this VCM is something different. The same only. So see a VCM, RCM, the position. This is the position. Now going to give you the velocity of the center of mass. It is R1 V1 plus R2 V2 goes on Vn. That's exchange. It's multiplication same only, no. So Vn Rn by the total velocity V1 plus V2 plus goes on till V on. Okay, clear? Shall we move to the next formula? Now, this is the third formula, correct? Now, so fourth formula I'm going to write. It's a kinematic equations. Kinematic equations. Okay, kinematic equations. You have already know what is omega, what is alpha, what is theta. It's the angular perspectives of the uh, linear systems. Okay, so if you take for omega, it's angular perspective of v velocity, and if you take theta, it's angular perspective of displacement. If you take alpha, it's angular perspective of acceleration, like that. Okay, so how can I write the first equation of motion? It's omega naught v. Okay, final velocity equals to initial velocity plus acceleration into time, and its second equation is theta, displacement equals to ut plus half at squared. Remember these things, omega square minus omega naught square equals to 2 alpha s. So this is the fourth equation. Shall we move on to the fifth equation? Now the rotational analog of the force, we can say it as torque, correct? The fifth equation, torque. So torque we will represent as tau, correct? So this tau is the moment of force. Are you clear? Moment of force is what? Tau. So you can say it also turning effect of force. Okay, turning effect of force, the magnitude of force, the turning effect of force is what? The torque. So how can you write the formula? Torque equals to force into perpendicular distance. So this is one formula for torque. Also it's the rotational analog of force. So it is moment of inertia into moment of mass into acceleration, I into alpha. Clear? Are you clear? Two equations are there for torque. You should note these things. Okay. Now the unit you have to know. No? Newton meter is the unit of torque, and the dimensions is mlt minus 2. The same as the force. Okay, mlt minus 2. And the next equation is power. Rotational analog of power is torque into omega. So the what is the linear analog? It's force into velocity. So that's what? Torque into omega. Are you clear? So one more thing you should know about couple. Couple is the combined torque. One torque on this side, one torque like this. If you see the car drivers, no, this is what the couple. Okay, clear? That's what the couple. And you can say twice of torque, but it's not a correct definition, but you can remember in that way. Opposite torques. One torque is this way, one torque is this way, like that. Now, what's the next equation? Relation between angular momentum and angular torque. Oh, okay, torque. Okay, angular momentum. Angular momentum. How will you define momentum? Angular momentum, and then torque. Relation between angular momentum and torque. So before that, I will tell you one more thing. You know that force is change in momentum, linear momentum, correct? Change in it. The same way torque is change in angular momentum. Completed? Okay, are you clear with this concept? And it's also applicable to the conservation of angular momentum. Okay, the same way of linear momentum. And I told you here moment of inertia, correct? What is moment of inertia is? Moment of inertia is m1 r1 square plus m2 r2 square. See, this is the position of the center of mass. This is the the rotational analog of mass. This is the rotational analog of mass. Rotational analog of mass. Okay, clear? That's what moment of inertia. Moment of inertia is goes on till mn rn squared. Are you clear? So 8 formulas we have covered. And one more equation for angular momentum is linear momentum into the distance. What is this distance? It's perpendicular distance from the axis of rotation. Like if you say this is the ring, I'm going to teach you the axis theorem, perpendicular axis theorem, parallel axis theorem. Now if I take the ring, so if this is going to be the axis, okay, the center is going to be rotated. So this is what the axis. I keep my hand and rotate this this page. This is what my axis, okay, the axis of rotation. So perpendicular, sorry, linear momentum into the distance from the axis of rotation, okay. This is the angular momentum. And then work you have to know, work is torque into theta. And the angular momentum is a vector quantity. You can write it as p d sine theta. The theta is the angle between the components, okay. Means the x coordinate, and this from where if you take going to find the angular momentum of this point, this is the theta, okay, clear. So this is what the formula. And the should know that moment of inertia depends on the dependency of moment of inertia also you should know, okay. So it's also maybe the MCQ you can be asked. So mass of the body, the first point is mass of body. The second point is size and shape of the body. Mass of the body, size and shape of the body. And the third point is distribution of mass, okay, distribution of mass you are going to see. And the fourth point is position and orientation of the axis of rotation with respect to the body, okay. Distribution of mass, distribution of mass, and the fourth, distribution of mass from the axis of rotation. Likewise, position and orientation of the axis of rotation. Position of axis of rotation, okay, rotation. Now relation, now we will move on to the 10th formula. This is the relation between, I will put points over here because you know confused, no. Okay, the relation between the moment of inertia and the rotational kinetic energy. It is moment of inertia is equal to 2 times of rotational kinetic energy, okay, 2 times of rotational kinetic energy. This is what the equation. And you can say that 2 times of moment of inertia is the rotational kinetic energy. Rotational kinetic energy is the formula. What is the formula for rotational kinetic energy? Is half I omega squared. So the moment of inertia and the rotational kinetic energy are related in 2 ways, okay. So this is one formula for rotational kinetic moment of inertia. This is one formula, okay. So next is the radius of gyration. The radius of gyration is if you take so wait, this is the axis. If you take if I rotating this plane over here, I want to rotate this plane from this axis, is the radius of, if the radius of gyration is this, you can say it as a mean distance of the total mass, okay. Moment of inertia equals to mk square. What is this is r1 square plus r2 square till n by n. So this is the mean value, correct. So mean distance of the total mass, you can say moment of inertia is the radius of gyration times the total mass, okay. This is the moment of inertia. This is the 11th formula, radius of gyration formula. Now we are going to enter into the perpendicular axis theorem. Perpendicular axis theorem is easy only. So if you take, this is a system of particle and the axis is in this way and the x-axis, okay. This is y, x, z. Now if you want to find the moment of inertia of this z-axis, okay, how will you do means, if the rotation is in this way, how will you find means, the moment of inertia in the y-axis plus moment of inertia in the x-axis gives the moment of inertia in the z-axis. Next is the parallel axis theorem. Parallel axis theorem. Parallel axis theorem, the same. I'm going to take the system of particle, one axis in this way, and the same plane I'm going to another axis in here. So if I'm going to rotate over here, this is one axis, and this is another axis parallel to this. If I find this axis moment of inertia, I can easily find this. How? Means mr square should be common. Mr square is common, plus if this is the moment of inertia have find, you write it as id. Then if you want to find this moment of inertia, take it as a, you take it as d, ia, you can find it. So that's what the parallel axis theorem. They are parallel to each other. mr square will be common, and if you find one axis moment of inertia, you can easily find the next axis moment of inertia. Okay, clear? Now if you are going to apply this in the shapes, I will start it in the next page. First, you will be starting with the ring. If you know one formula with a particular shape, you can find many other formulas with the axis. So first